and welcome to Kings of Curiosity. It's the place where we talk about amazing ideas which could shape all our lives in the future. We're here to take you down a road of discovery as we talk to some of the brightest minds in Britain today to understand what they're doing and why their ideas matter, because they can help us to understand the world better and hopefully make it a better place. So today, we're going to be looking at one of the hottest areas of science today, where science is starting to turn into science fiction. That's quantum computing. Now, quantum's a word which conjures up all kinds of strange ideas and phrases, from charmed quarks to even time travel. And I've been thrilled to discover that Cambridge has been a leader in a lot of the research that's been driving quantum computing for several decades now. But like any new area of scientific discovery, along with the very justified excitement, there's also a lot of overhype and a lot of confusion and a lot of people going, what does that mean, really? So what we're going to try and do today is demystify some of this, explain what quantum really is and also what it isn't, and give some sense about where it's going for the future, or at least what the big challenges and questions are today. And I have someone today who's been working in this field for years, David Arvidsson Shukur. He's at the Hitachi lab, and so he's here today to tell us what quantum really is and what it isn't. Welcome.
Thanks for having me, Gillian. Pleasure to be here.
You must get a lot of people asking you all the time, what on earth do you actually do? What is quantum computing?
Yes, this does happen that I get this question, and sometimes it's the opposite of an icebreaker, but sometimes if I feel warm in my shoes, I'm able to give a good reply to this. So
imagine you're trying to tell your friends or family or your mother, what on earth is it you're actually doing with quantum?
Well, so what I'm personally trying to do is to develop theory that will allow us to build a new type of computer that can tackle specific problems that with standard computers that we have today are hard to tackle or solve. And the tools that we use in order to try to build this machine, known as a quantum computer, is the tools developed about 100 years ago when researchers, scientists, physicists started to uncover the strange behavior of small particles known as quantum particles.
Now, as I understand it, and I'm not trained as a scientist, I was an anthropologist originally, until about 100 years ago, everyone was obsessed with another graduate of Cambridge, Isaac Newton, and that defined how people looked at physics. What happened 100 years ago to change that?
Yeah, this is absolutely right. So 350 years ago, Isaac Newton wrote down a number of equations, and these equations kind of described everything that had happened before in experiments and almost everything that happened for the next 250 years. And 100 years ago, something really revolutionary happened. Experimentalists had gotten so good at doing physics experiments that they could start doing experiments with the smallest constituents of our universe, so atoms, electrons, individual particles of light known as photons. And what the experimentalists saw then were things that were really hard to explain, actually impossible to explain, with the laws of Isaac Newton.
Well, I'm always fascinated by Isaac Newton because a little-known factoid of King's history is that Newton actually wanted to be Provost of King's himself and was turned down. I think politics had something to do with it, but anyway. So what you're saying is that Newton had these theories, they dominated physics, and then some people came along and said, maybe this isn't quite right. Who were those people who were trying to basically challenge Newton?
Well, from a theoretical perspective, it was kind of spearheaded by a number of people, ranging from Albert Einstein, Irving Schrödinger, Heisenberg, but also people here in Cambridge like Paul Dirac. And of course, the experiments that led up to these discoveries were also tied into things that had been going on here at Cambridge in terms of doing experiments with individual electrons and atoms.
So Schrödinger is well known because of his cat. And I've been told that that helps to explain a lot of the ideas behind quantum. Newton is best known for having developed the law of motion. And yet In the 1920s, people like Dirac began to create equations which suggested that the law of motion wasn't as universal and didn't explain everything in quite the same way that people had expected.
Yeah, that's right. So if electrons in atoms, so these small charged particles that go around the nucleus, behaved, for example, like the moon behaves when it's going around the Earth, the electrons could basically be wherever they wanted in relation to the nucleus. And pretty soon after the discovery of atom experiments, it was clear that electrons could not be exactly wherever they wanted. There were some additional sets of rules that decided where the electron could be. And it was in trying to describe this physics, so these new restrictions, that a lot of the strangeness of quantum particles were developed. So once that theory by Schrödinger and Heisenberg was in place, people started to realize that there were even more strange behaviors about these particles. So, for example, you could have a box with two compartments, and an atom, a single atom, could in an experiment behave as if it had been in two places at the same time, which is obviously something that with our standard intuition and logical sense is very, alien. And it was behavior like this that Schrödinger tried to encapsulate with his analogy of the cat. So he was basically saying that if the cat was behaving like a quantum particle, like an atom, then, well, it could be two things at the same time, so dead and alive at the same time.
So it's a really radical way of imagining the world. I mean, it does sound an awful lot like Doctor Who or Star Trek. But, as you say, it's revolutionized a lot of how we look at physics and how we try and imagine some of the underlying mechanisms of subatomic particles.
Yeah, that's right. And there's really been three revolutions when it comes to the development of quantum mechanics and quantum physics. So the first revolution was a purely scientific one, about 100 years ago. So 1925, 1926, Schrödinger and Heisenberg write down their independent analysis of these experiments and changed the way we thought about physics from a fundamental point. And then with that increased theoretical knowledge and the fantastic progress in experiments also came the ability to make smaller and smaller electronic components. And given that we now knew how small things behaved, we could make very, very fine-tuned small electronics. And this is what's sometimes known as the quantum revolution of technology, which is the creation of the technology that's in our computers today, in our iPhones. Now we're at the basically doorstep of yet another quantum revolution, which is the revolution of trying to not only build electronic components of small things, but actually process the information using the behavior of quantum particles themselves.
Wow, that's fascinating. So we really are on the verge of this third revolution. And I'll come back and ask you a bit more about that in a moment. But before we do, we're sitting in my study in King's College next to a big photograph of Alan Turing, who actually lived a few feet away on staircase X when he was a student and did a lot of his studies and works here in King's College. Did Alan Turing play any role in all of this, or was he just working on artificial intelligence? Is that connected to any of this or not?
Okay, so let me dissect that a little bit. So Alan Turing obviously was a founding father in the field of computing. Basically at the same time that we were learning more about quantum particles and quantum experiments, society was transformed by the inventions of Alan Turing's electronic computers. And already from the beginning, it was clear that a certain type of problems were very hard to solve, even if you managed to build one of these Alan Turing computers. And these problems often had to do with simulating or modeling quantum particles. So for example, molecules in pharmaceutical medicines or in catalysts or components of batteries, they are at the fundamental level made up of small quantum particles that act in a fairly alien way to everyday things. And it was clear very early on that these are hard things to simulate, even with a strong normal computer. And this realization that eventually led an American physicist called Richard Feynman to give a lecture titled something like Simulating Physics with Computers. And Richard Feynman, he knew that it's a very, very important thing to be able to simulate things like molecules for society as a whole. And B, it's very hard to do that with normal computers. And his simple suggestion was that if we want to build something that can simulate the workings of molecules, then maybe it would be easier if the fundamental architecture that did that simulation was made of quantum particles itself. So he suggested, let's build a computer that has its individual components as individual atoms that do the computation, and maybe that device will then be able to solve these very important problems. So there's like a direct lineage from the discoveries of Alan Turing's of computing into what we're now trying to do with the quantum computer. There are other quirky facts about Alan Turing and quantum mechanics. So when we think of Alan Turing, we think of this, information theory genius who spearheaded this fight against the Nazis and on the intellectual computational level. But if you go and study his letters to friends and colleagues, you'll see that being embedded in the ecosystem of Cambridge and intellectual Britain, he was very well versed in subjects, for example, quantum mechanics. And there is a very famous quantum effect called the quantum Zeno effect. And I'm not going to go into exactly what that means, but it plays a very important role in the removal of errors in quantum computers. And if you track back the earliest scientific description of that effect, you will find that it occurred in a private correspondence letter between Alan Turing and one of his friends.
Wow, that's fascinating. Well, we actually have a lot of the Alan Turing letters here in the archives at King's, and we've been fortunate enough recently to acquire some more material, and it's really electrifying just to look at these early letters and scribbles and even his diaries from school, which show how his mind was developing. And I must say, I really take your point about the fact that the Cambridge ecosystem has these colleges which jam together different types of disciplines and brilliant minds into a small space. It's a bit like a chemistry experiment where you take molecules from all over the periodic table and shove them together under pressure and see how they interact. And we can see that every day here in King's with people bumping into other people from different disciplines and talking. But the fact that even Alan Turing was benefiting from that kind of collision, serendipity inside Cambridge is fascinating, I must say.
Yeah, I agree. And it's fascinating on the individual level because, it's a very kind of stimulating environment. But I think it's also, highly beneficial for the academic and scientific endeavor, right?
I sometimes talk to people who've worked in American universities that, of course, are brilliant and have many strengths. But I gather that if you are a researcher in one department, you tend to just talk to people in your field, whereas here you're forced to collide with the unexpected.
I agree. It's like a really marvelous artifact of living in Cambridge.
I'm curious, what made you come to Cambridge or stay here? Because I'm quite sure you would have had lots of other options.
Yeah, so I think there are three things that made me come and one thing really that makes me stay. And the three things that made me come, so first of all, my wife is based near Cambridge. So,
very, very good reason.
Yeah, and then the second reason is that we have these giants here in Cambridge, like, Bertha Swirls, Paul Dirac, Rutherford, Brian Josephson, Richard Jose, Crispin Barnes, that attracts you to a place. And then the third reason is what you touched on before with this kind of intellectual kitchen where you're put in a college, you meet people from loads of disciplines of science and outside science, and You just
you cook up something with all these different ingredients, to use that analogy. Yes.
It's hard not to want to come to Cambridge. It's also very, very beautiful. I mean, this room that we're sitting in is just magnificent. And then what makes you stay in Cambridge? I think the one thing that we in the Hitachi Cambridge Lab really, really, really benefit from, and that I really treasure, is the fantastic quality of the PhD students here. I have never come across a place with such an abundance of truly brilliant, hardworking, fun, and charismatic students.
Wow. So basically they're cooking up new recipes for the future, because you've got all these brilliant minds together in close quarters, bumping into each other and having a chance to, react and interact with each other, a bit like a bunch of quantum electrons, or I'm sure I've got the wrong word there, but quantum molecules.
Oh, it's perfect. Yeah, that's it. And it's something that I have visitors coming from America, from Asia, from all over Europe. And this is the one thing they usually say when they're taking off, that they envy the quality of the students that we have here.
So Cambridge is actually a human version of a quantum experiment in itself.
Yeah, that's right. But when I joined King's as a student in 2013, one of the older fellows told me that being a student at King's College is not only about excelling in your degree of fundamental physics, it's also learning about how to have a conversation about the French Revolution whilst consuming more than one bottle of wine in an evening.
That's a fantastic description, isn't it? And actually, there's a real benefit to eating and talking and learning the world through conversations like that. And the chance conversations can often be some of the most powerful ones you have. There's quite a lot of research that's come out, actually, from people bumping into other people over dinners or lunches here in the college, which is very exciting. But when you look back at the story of how quantum's developed, I mean, you've got a lot of the most famous names, which even I as an anthropologist have heard of, like Richard Feynman, like Schrödinger. You've also got some people in Cambridge who've been involved in driving the revolution more recently, haven't they?
Yeah, so maybe let me pick up from where I stopped before when I was talking about this lecture by Richard Feynman. Right? So Feynman had this vision: we really want to solve these difficult problems that are really important for society, related to simulating molecules. And that gave the field a slow kickstart. So some people around the globe started thinking about, okay, so how would this work? And in the late 80s, early 90s, two chaps, so David Deutsch and Richard Josa. Richard Josa is now a fellow here at King's College, Cambridge. And they wrote down a small theoretical analysis where they looked at a simple mathematical toy problem, a problem that's rather hard, or actually it's very hard to solve with a normal computer. And they showed that if you could use quantum particles to encode and manipulate the information, you could solve this problem very quickly. And unfortunately, it's a useless problem for society, but it had a huge impact on the field of physics and computer science, because it showed that Richard Feynman's intuition that some problems might be easier to solve with quantum computers than with normal computers was true. And this really led to yet another increase of enthusiasm for the field of quantum computers.
Right, because I've been told that the Deutsch-Joyce algorithm is one of the founding pillars of this entire quantum discipline.
Yes, that's right. So the Deutsch-Joyce algorithm is the first really strong instance of, for this completely useless problem, to academics showing the scientific community that here is an algorithm that if you try to run it on a standard computer, it will take a very long time, what computer scientists refer to as an exponential time, whilst if you run it on a quantum computer, it would be solved in just a single step, basically.
Wow. Well, I must say, one of the most electrifying conversations I've ever heard while I've been at King's is between Richard Josa and Hermann Hauser, talking about the potential for quantum. And I think I understood only half of it, but it was just fascinating to hear their excitement and how these ideas have developed.
And the ideas have really developed. So the Deutsch-Jones algorithm stems from the late 80s, early 90s. And just a few years later, Peter Shor, who's now professor at MIT, looked at a problem that has more use to computer science, namely factoring large numbers. And he showed that the quantum computer could factor large numbers much faster than the standard computer. 2 years after that, Love Grover showed that the quantum computer could search through trial and error solutions with not a huge, but a significant speed up compared to standard computers. And in the same year, American physicist Seth Lloyd showed that Feynman's original intuition that quantum computers can model and simulate molecular behavior better than normal computers was true when Seth Lloyd wrote down an algorithm of precisely how you would go about doing that if you were able to build a quantum computer.
So it's an amazing roll call of names, and some of these people are not yet household names. I dare say they will be in the future, but it's really interesting to hear how Cambridge has been part of that galaxy of people driving forward these ideas. And I'm curious, so today you are working in a lab with Hitachi, the Japanese company, to try and push forward some of these ideas and boundaries. Now, there's a lot you can't talk about to do with your research because it's a very competitive field and there's a lot of things changing fast. But tell us a little bit in general about how it came about that you're working there.
I think there are two levels to this. So it's like the personal level and also the development of this lab. So maybe let's start with the development of this lab. So I think it's more common in America than in Europe and the UK to have these privately funded embedded labs. So the Hitachi Cambridge Laboratory is, as you say, funded by the Japanese company Hitachi.
Which, by the way, I should say I love because I lived for years myself in Japan and I have a huge affection and respect for Japan as a country. And what some people in the West don't know is that actually they've been really at the forefront of a lot of the robotics and, to a certain degree, the AI revolution as well in recent years.
Yeah, and I agree. And it's like they really have this sense of value for the intellectual developments of technologies. And in the 80s, Hitachi, the company, thought that it would be a good idea to start an embedded laboratory at the University of Cambridge. So in the 1980s, they did that. And in the beginning, this laboratory worked together with the university on the development of things like solid-state hard drives for standard computers. But about 6 or 7 years, Hitachi as a whole grew more and more interested in this emerging field of quantum computing. And it was at that point, Hitachi Cambridge Laboratory was targeted as one of the places where the company should try to develop this quantum computing technology. And shortly after that, I was lucky enough to be hired as a researcher. At the moment, there is both a theory team and an experimental team. So we have an experiment team that is trying to develop the hardware to actually build a quantum computer, whilst myself and colleagues are trying to develop algorithms and theory of what you could do with the quantum computer when it's there.
And so the idea is to essentially create a whole new type of computer in the future? Is that the kind of goal, overarching goal?
Yeah, so at the moment, we mentioned these algorithms, so the Deutsch-Jones algorithm and this molecule simulation algorithm by Lloyd or the factoring algorithm by Peter Shor. So at the moment, we have a few targeted algorithms or mathematical problems that we know that a quantum computer could be faster at solving than a standard computer. And the hope is, of course, that this list will be able to be made much, much longer so that there are more and more problems that quantum computers can solve faster. And the goal is, as you say, to try to build this machine and see what happens. It's a really intriguing task, both from an industrial perspective, because the benefits of solving molecular simulations are so vast, but also an intriguing task from an academic and scientific perspective, because quantum physics and quantum computing is one of the few areas of science where we really, really know very little, and where there's still big debates between the leaders of the field of what's happening and what's the correct way of explaining things.
So it's a really hot area for research, cutting edge research, and lots of potential for brilliant minds to basically push the whole sector forward in the future.
Yeah, that's right. I think when I started my PhD in 2014, it was not perceived as a very strange thing to be doing a PhD related to quantum computing, but I was warned by several people that it might be hard to find a postdoc or a more senior position afterwards, whilst now it is, as you say, one of the hottest topics. And that's really fantastic because we have the entire world trying to build this thing. It's great for the scientific community, but I think on the individual level of some of our PhD students, it can be scary because they need to get a few papers out to get their PhD thesis done, and they're competing with thousands and thousands of people.
Wow, fascinating. Now, one of the things that you're working on, as I understand it, is the concept of quasi-probabilities and negative probabilities. What on earth does that mean?
So this is one of my favorite topics of research.
So everyone listen up, because it's going to make you sound incredibly smart the next time you talk to anyone about quantum computing.
It dates back to the first decades of the development of quantum physics, so almost 100 years ago, when a chap called John Kirkwood at MIT and Paul Dirac here in Cambridge tried to explain some of the phenomena you could see in quantum experiments. They noticed that if they tried to use the tools from standard statistics to explain the things that happened in these experiments, they failed. They just couldn't get normal probability theory and standard statistics to explain these things. Maybe let me give you an analogy. So say that we have a city with a bunch of cars driving around, and I could then do experiments to find out what's the percentage of cars that drive around 30 miles an hour on King Street. And maybe I would find that in Cambridge there is 0.01% of the cars are currently driving around 30 miles per hour on King Street. When John Kirkwood and Paul Dirac tried to do similar theoretical descriptions of experiments with electrons that maybe were moving around in a little chip, they noticed that they couldn't assign probabilities to these electrons. But if they changed our laws or our rules of how to do statistics or probability theory a little bit, by allowing the probabilities to take negative values, which, sounds crazy. What does minus 5% mean? But if they did that little change in the way that they did the maths, then the end results that they got out actually matched what they saw in experiments. So standard probability theory is what we're used to, probabilities between 0 and 100%. In quantum mechanics, we can describe things using these things called quasi-probabilities, which can take negative values. So you can have something like minus 5%. And Paul Dirac, who of course was one of the spearheads in finding the positron, so the positive equivalent of the electron or the antimatter equivalent of the electron, which he actually found by writing down equations to try to model particles like the electrons, and he saw that there was one negative solution and one positive solution, and then had that confirmed in the discovery of antimatter. He took these negative probabilities very, very seriously. So he once said, negative masses or probabilities should not be considered nonsense. They are real physical things and should be considered somewhat more like a negative of money.
Wow, it sounds fascinating and really exciting. It's also quite mind-bending. It's very Star Trek, in fact. Were you a Star Trek fan? Were you a Trekkie growing up?
I wasn't, actually. I was very kind of Russian literature,
Right. So more like
far
Asimov
away
and
from the
stuff.
sci-fi. But I guess I got my fair share of sci-fi from quantum mechanics.
Because they actually have, people have actually said jokingly that quantum will enable time travel and things like that.
Yes, so I think there's a lot of maybe over mythology.
Hype, yes.
Yeah, it's a bit of an overhyping of the field, but there is a small element of truth to this, that a lot of people, including myself, have investigated in a very rigorous way in our research. And it stems from one of the most fundamental aspects of quantum particles, a phenomenon called entanglement, which is basically the phenomenon of if you take two quantum particles, like two atoms, and you bring them close together so that they feel each other's force field, and then you separate them, then these two atoms will have both their future and their past somewhat interconnected. It's not in the way that you can use these particles to send information faster than the speed of light, but if you use these particles in experiments, you will notice that it's very, very hard to reconcile the things that will happen to these particles in the future if you try to explain it with a model that doesn't allow for any kind of time travel.
Wow, that's mind-blowing.
It is really mind-blowing, and it's kind of it's also very frustrating from a kind of curious point of view, because so we can do these experiments that show that if we believe that the quantum equations we have correspond to something real, then there seems to be some sort of time travel going on, but that time travel is hidden from direct use. As I said, if you could really time travel backwards in time, then you could send information faster than the speed of light. But it turns out that when we try to do that in experiments, the universe is kind of conspiring against us and throwing in some random natures of the experiments just enough to hide that.
So we're not in Star Trek yet, sadly,
Not
or
yet.
maybe just as well, actually. But so there's a huge amount of hype around AI right now. Inevitably, people in the investing community are having a lot of hype around quantum as well. And journalists sometimes jump on stories and overhype them too. Do you think we're in danger of having too much hype around quantum?
So I think this is a very good and important question. So first of all, I'm incredibly happy that there is a lot of hype and enthusiasm towards quantum computing, because it means that, you know, we have the means to look into this extremely interesting physical problems that might transform society, right? So at the first step, it's a very, very good thing. But as you allude to, there are some issues with overhype, and I can give you a few examples, or maybe two examples. So the first thing to say is that at the moment, there's a very specific set of problems that quantum computers would be faster to solve. Sometimes when you read popular science on quantum computing, you get the impression that quantum computers will just be faster than normal computers. And that's not the case. For many tasks, they're likely to be slower. There are some specific tasks. Some of these tasks are very important, where quantum computers would be faster. And then you get also some popular science stories that are just plainly wrong. So, for example, if you're trying to optimize a component of your business, a common mathematical problem that you have to look at is something known as the traveling salesman problem.
What's that? That sounds kind of weird.
Yeah, so the traveling salesman problem is basically you're tasked to go and sell vacuum cleaners or something at 50 cities scattered across Europe. And you're going to go by car, and you want to burn as little fuel as possible, and you only want to stay in each city once. So it's the simple problem of finding what is the shortest route to visit all of these cities. Or is there a route where I can visit them in less than this distance?
So it's kind of optimization challenge, if you like.
Exactly. And it turns out that loads of optimization problems like warehouse storage and stuff like this can be mapped onto the traveling salesman problem. So if you can solve the traveling salesman problem quickly, then you know you can solve a lot of important things.
Absolutely.
And sometimes when you read the news now, it seems that quantum computers could have this exponential speed up in solving the traveling salesman problem. But we have very strong mathematical indications that that is not the case.
How interesting. I mean, it strikes me a little bit like some of the hype around a technology like blockchain, because when blockchain came out, everyone got really excited and said this could make everything work faster and, you know, be more effective. And in reality, what's become clear, at least in the world of finance, is that in some contexts, blockchain can be useful, but it can't be used for everything. I mean, obviously, quantum is in many ways far, far more important than blockchain. But this point about it being used in some contexts, but not everything, I don't think has been widely understood.
Yeah, and I think it's important to get that message across to avoid overhype, as you say. And we're in this beneficial situation of having some algorithms like the simulation of molecule algorithms that we are very confident will be very useful in the future. But then, as you say, there are some areas which we pretty much know we won't be able to help out. And then, of course, there's the big anticipation of what will we discover when we have a quantum computer? Because now we're kind of doing science in the dark a bit when we're trying to write algorithms for problems. It might be that once we have a fully functioning quantum computer, finding new areas where we could use it will be much easier because you can then just program it and see if it works.
In terms of practicalities, are we actually going to see a quantum computer anytime soon?
So there are two ways to answer this question. The first way is to say we already have some quantum computers at the moment. They range in size and abilities. Just over 10 years ago, people were saying it's going to be a very long time before we have even a prototype quantum computers. And just a few years after that, we had one. And it's companies like Google, IBM, and Rigetti, just to name a few, that have really done amazing engineering feats and developed these prototype devices, which allows you to do stuff with them. Now, these prototype quantum computers are extremely prone to disturbances from the outside world. And as soon as they're disturbed, they start working worse and worse. And unfortunately, the current hardware that's out there is not good enough to solve these useful problems that we want to solve. But this is really what the field is focusing on now. There are two ways we're trying to tackle this problem. One is by making the hardware more robust to noise and better. And the second way is to make algorithms, so things that will actually run on this hardware, easier. So with this kind of two-front approach, we're trying to bring the time to actually useful use of quantum computers.
Right, because the way I can see it, it seems like the problem with the computers at the moment is that they're a bunch of sensitive flowers that basically malfunction or create errors if they get disturbed. And so you have to basically find a way to take out the errors that keep cropping up. Is that a layman's way of explaining it?
Yeah, I think that's pretty good. So again, I talked about the universe conspiring against us to use some of this quantum stuff. And here again, in this development of quantum computers, we can see one of these universal conspiracies. So normal computers, they also have errors when you're trying to do something. But what the normal computer does is that it copies the information and then it does operations on many of these copies in parallel. And then basically it does a majority vote in the end. So if there's been errors on some of these, the majority vote will average this out. But if you try to copy quantum information, so once you've encoded information on a quantum computer, you will notice that that's not possible.
Precisely because we have the Schrödinger's cat problem that, you never actually get the same replica all over again and things are existing on multiple planes.
It's related to that, and it's related to another famous analogy of Werner Heisenberg's, which is related to something called Heisenberg's uncertainty principle, which tells you that you can never know exactly where you are and how fast you're going.
Which is pretty hopeless if you're trying to copy something.
That's right.
Yes.
And this has led to this field known as quantum error correction, which is, given that we can't use exactly the tools we use for error correction in standard computers, how do we do that in a quantum computer?
To put it in completely layman's terms, it's a bit like you've got a bunch of computers that go off and have tantrums every 2 seconds like a toddler, and you're trying to find a way to discipline them and get them back.
Yeah, that's right. Although it's more like 1,000 times every second.
1,000 toddlers having tantrums all at once. Yeah. And then you're trying to create some kind of order and physics experiment to copy that. And of course, the point about toddlers like quantum atoms is they're somewhat unpredictable.
Which is the charming thing about toddlers and quantum particles.
Well, also very, very exciting if you can get them under control. One of the things that's created some of the hype, but also the fear around quantum computers, is the idea that if anyone actually creates one that really works well without errors, they're going to be able to hack into every other computer in the world. And all of our encryption systems linked to bank accounts or private data and things like that will evaporate overnight. Is that a real risk anytime soon?
So it's hard to know when this will happen. Basically, it will happen when we have a fully functioning quantum computer. Just to give a bit of background to this, so modern encryption schemes are, as you say, at large based on something called the RSA scheme, which uses integer factorization as a part of the encryption. In basic terms, it's related to, if I ask you to tell me what two numbers, when multiplied together, gives me the number 187, even if I give you a calculator, it will take you longer time to solve that problem than if I ask you to multiply 11 and 17. Mm-hmm. So this is the underlying mechanism of how modern day encryption works at large. And this algorithm from 1994 by Peter Shor showed that for a quantum computer, these two problems, so finding the two numbers that multiply to give you a number, is as easy to solve as multiplying two numbers.
Wow.
So in principle, if we were able to build a quantum computer, we could tap in on a lot of today's encrypted messages and decipher it and read what says there. And something that's often not appreciated by people is that also if someone were to collect encrypted data today, they would be able to decipher this in the future when there is a quantum computer. So that might also be something that companies and governments will bear in mind. And it is something that has in the recent years started to gain more attention. So how do we mitigate this? Well, there are different ways to encrypt data, and at the moment researchers are trying to develop other ways of encrypting information that does not rely on integer factorization. So we could try to encrypt information with problems that would be hard to solve even for a quantum computer. And then it would probably be safe for a bit longer.
So we ought to all be grateful that the research is still not quite there in terms of producing the quantum computing, because it gives us time to protect ourselves before someone actually creates a quantum computer.
Yeah, depending on your kind of moral standing in society, I guess some people would really like to tap in, whilst, yeah, for you and me, it's probably good if...
Right. Well, that's good. So I know that one of the hot topics in this field are so-called quantum chips. And we all learned about silicon chips in recent years and how critical they are to the global economy and all the things we rely on today. What is a quantum chip?
So a quantum chip is the fundamental building block for some of the contenders for quantum computers. And Cambridge has played a kind of pivotal role in the development of many of these quantum chips. So for example, companies like Google and IBM, they're trying to build their quantum computers not using atoms, but using artificial atoms. So small chip components that behave like atoms. And these components are made out of a bit of superconducting material, which is basically a material that can carry electronic charge without losing any energy. And then they have a small component called a Josephson junction. And it turns out that if you put in the small Josephson junction in a superconducting chip, you can make that chip behave like an artificial atom. And Brian Josephson, of course, is Professor Nobel laureate from the physics department here in Cambridge. So Cambridge has had a very pivotal role in enabling that chip technology. At the moment, my lab, the Hitachi Cambridge lab, under Charles Smith and Andrew Ramsey, are developing and doing experiments with silicon chip technology. So silicon is a semiconducting material. That means that sometimes it acts like plastic, sometimes it acts like metal. And if you do exactly the right things with this material, you can trap individual electrons in a grid in this silicon chip. And then these individual electrons are quantum particles. And if you can move them around and control them in the right way, you can then do quantum computation in these silicon chips. And as I said, the scientific community are currently looking into many technologies for how to build a quantum computer. And there are many exciting venues. But the reason I think that my lab is looking into these silicon chips is that we already, as you said, have a big infrastructure for producing silicon hardware for standard computers. So if, it turned out that we could build a quantum computer with silicon, then a lot of the infrastructure would already be there.
It's absolutely fascinating what you're saying. And it's actually rather appropriate that we're talking about this sitting next to a big photograph of Alan Turing, because I rather suspect that if anybody had been doing a podcast with Alan Turing back in the 1930s, they might have thought that a lot of the ideas he was coming out with back then were either mad or crazy or unworkable. And of course, his name was not a household name back then. And they would have just had a glimpse of the fierce intellectual debates and experimentation was going on around that at the time. And in many ways, quantum feels a bit like the early days of AI today in terms of the fact you're trying to really break through new boundaries, but in ways that most people in the public don't understand at all.
Yeah, I think this is a good way of putting it. And as you said, like some of the ideas of Alan Turing would have sounded alien to us, 100 years ago. We are now discovering that some of the ideas, for example, I mentioned these negative probabilities that Paul Dirac was really highlighting at something that we need to try to understand. So in the last few years, I've been lucky to be a part of a multinational research collaboration where we're looking at these negative probabilities that Dirac was so obsessed with. And in field after field of quantum technology, we've been able to show that where you can get quantum advantage, this is really in the experiments and in the technologies where you harness these negative probabilities.
Wow, gosh.
In the last month, we put out a preprint on Archive together with colleagues where we actually pinpointed for the first time that exactly this framework of Dirac's, with his framework describing negative probabilities, can be linked exactly to the algorithms that could give you an advantage in quantum computation.
Amazing. Well, congratulations. Of course, one of the whole points about Alan Turing's story and the whole range of issues he worked on is that, you as scientists are essentially sowing all these intellectual seeds, and you don't know what the harvest will be in the future, but you just keep scurrying along quietly, often without any public recognition, just sowing these intellectual seeds. And we hope that there will be a fantastic harvest.
Yeah, I think this resonates with me, because at the end of the day, what motivates most of us and most of our students is curiosity. Of course, it's really nice to be working in a field like quantum computing where we think that it might have really big societal impact. But at the end of the day, what motivates us is really an eager lust to understand how these strange particles behave, which after 100 years of research, we still don't really understand.
What advice would you give any young students, any young wannabe Richard Feynmans, Alan Turings, anyone who's listening who says, wow, this sounds so exciting, I want to get engaged with this? What advice would you give them?
So maybe I have one boring advice and one less boring advice maybe. So the boring advice is if you're really interested in science and pursuing a career in the theoretical part of science, then study as much mathematics as you can. So I think a solid mathematics background from pre-university and university years is really a ticket into a successful career later in life. And the less boring advice is maybe try to engage with people, go and visit universities, talk to academics, meet students, and learn what's going on. I mean, students today and young people are at the advantage of having YouTube. So actually you don't need to even travel. You can just tune into YouTube channels and find out what the latest news are. But by keeping up to date with these things, you will come across problems that seem very interesting and don't have a solution. And it's by thinking about these problems that we push science
Absolutely.
forward.
Well, that's the beauty of magic and science. And I guess a bigger question is, a lot of people don't really understand what's happening inside British science today or science in general. What can we do to get more understanding and respect and support? Because this is so critical to our future. And it's fantastic that Cambridge and Britain is playing a leading role in this field in quantum. But it really breaks my heart that people aren't out there standing up and saying high fives every day for what you guys are doing.
Yes, I think things like this podcast is hopefully a good way to kind of spread the gospel of British academia. But I remember my PhD supervisor, Crispin Barnes, he told me when I was about to go and do a postdoc in America that I would notice a very big cultural difference. And he was saying basically that in America, the Nobel laureates are, all over the news, they're famous, they're on TV shows, and they're very glamorous and outspoken. In the UK, the Nobel laureates is the old man in the office next door that you have no idea what he's been up to. So there is a bit of a cultural difference, and I think it's important that at some point we try to overcome at least the gospel spreading, because as you say, this is what will eventually drive more people into academia. And I think also popular culture has an important role to play here. When I talk to students and ask them what motivated you to go into science, it's often having read popular science articles or just fictional books that have raised some of these topics that are being researched.
So David, thank you so much for explaining what quantum is and also, frankly, what it isn't. It's a topic I think we all need to know a lot more about in the future. And it's certainly a topic we should be celebrating and championing and, yes, funding for the future as well. So I'll just end by saying good luck. We're all really proud of what you're doing and your teams are doing in Cambridge. And let's hope that you keep interacting with each other, with the rest of the Cambridge ecosystem, like a quantum experiment, to try and break new boundaries for the future.
Thank you. Thanks for having me.